A binary tree is a collection of nodes arranged in a hierarchy. Think of a family tree where each person can have at most 2 children. Node the basic unit that stores a value and links to its children. Root the topmost node like the trunk of a real tree. It has no parent. Leaf a node with no children comparable to a twig at the end of a branch. Internal node any node that is not a leaf it has at least 1 child. Degree of a node the number of children it currently has 0, 1, or 2 in a binary tree. Level or depth of a node how many edges you must follow from the root to reach it. The root is at level 0, its children at level 1 and so on. Height of a node the longest distance in edges from that node down to any leaf in its subtree. The height of the whole tree is the height of the root. Depth is often used synonymously with level. The depth of a node equals its level. These terms are the vocabulary that let us discuss performance balance and memory usage of binary trees, using everyday analogies like how tall is the tree or how many branches does a twig have. Binary trees come in many flavors, each defined by simple structural rules. Full binary tree, also called proper binary tree, every internal node has exactly 2 children. Imagine a perfectly organized bookshelf where each shelf that holds books also has 2 subshelves beneath it. Complete binary tree, all levels are completely filled except possibly the last, which is filled from left to right without gaps. Picture a tournament bracket where matches are scheduled row by row, left to right. Perfect binary tree, both full and complete, every internal node has 2 children and all leaves are at the same depth. It looks like a perfectly balanced pyramid of blocks. Balanced binary tree, the height of the left and right subtrees of every node differ by at most a constant, often 1. Think of a seesaw that never tips too far to one side. Degenerate tree, also called pathological tree, each internal node has only 1 child, so the structure collapses into a linked list. This is like a line of dominoes where each domino can only knock over the next one. Understanding these categories helps us predict worst-case operation times and choose the right tree for a problem. For example, heaps are complete trees and AVL trees are balanced. Maximum nodes for height h. In a perfect binary tree, the node count is n max of h equals 2 to the power of h plus 1 minus 1. Proof: each level I starting at 0 holds 2 to the I nodes, sum the geometric series. Minimum nodes for height h non-empty. A degenerate tree, a single chain has n min of h equals h plus 1 nodes because there are h edges from root to deepest leaf. Height depth bounds. For any binary tree with n nodes, the height satisfies log base 2 of n plus 1 minus 1 is less than or equal to h, and h is less than or equal to n minus 1. The lower bound comes from the perfect tree most compact, the upper bound from the degenerate tree most stretched. Node count in a full tree of internal nodes I. Since each internal node contributes exactly 2 children, we have n equals 2i plus 1. Rearranged, I equals n minus 1 over 2. Leaf count in a full binary tree, L equals I plus 1. Every full tree has 1 more leaf than internal nodes. These formulas are handy for sanity checking implementations. There are 2 primary ways to store a binary tree in memory. Array/heap indexing. Useful for complete or almost complete trees, for example binary heaps. Store the root at index 0 or 1, for a node at index I. Left child becomes 2i plus 1, or 2i if index starts at 1. Right child becomes 2i plus 2, or 2i plus 1 for 1 based. No explicit pointers. The position in the array encodes the relationship. This gives O1 access to any child or parent, but wastes space if the tree is sparse because many array slots stay empty. Pointer-based linked structure. Each node is an object or struct with fields. Value, left node pointer, right node pointer, and optionally parent. Works for any shape, dense or sparse. Memory usage is proportional to the actual number of nodes, O n space. Traversal needs pointer dereferences, which are constant time but slightly slower than array indexing due to indirection. In practice, choose an array when you know the tree will stay complete, like priority queues. Choose a linked representation for general binary trees, BSTS, of VL, red-black trees, etc. Both representations can be visualized with real-world analogies. An array is like a bookshelf where the position of a book tells you which books are on the left or right shelf. A linked structure is like a family photo album where each photo node points to the photos of its children. Tree traversal is the process of visiting every node in a systematic order. 4 classic orders are: pre-order, root then left subtree then right subtree. Create a copy of the tree, serialize a BSD for reconstruction. In order, left subtree then root then right subtree. Return sorted order for a BSD, useful for range queries. Post order, left subtree then right subtree then root. Delete or free a tree, children must be freed before parent. Level order, visit nodes level by level left to right. Find shortest path in an unweighted tree, heap operations. Complexity analysis. Each traversal touches every node exactly once. Time equals O of n. Space depends on recursion or auxiliary containers. Pre-order in order, post-order recursive use a call stack of height equal to tree height. O of h, worst case O of n for a degenerate tree, best case O of log n for a balanced tree. Level order uses a queue that can hold at most one level of nodes. At most ceiling of n divided by 2 nodes the leaves. O of n in the worst case, but typically O of width of the tree. Real-world analogy, traversing a tree is like touring a museum. Pre-order is enter the first room, explore every hallway on the left before the right. In order is walk the left wing completely, then see the central exhibit, then walk the right wing. Key left subtree less than key x less than key right subtree. This ordering lets us search, insert, and delete in time proportional to the tree height. Search start at the root, compare the target with the nodes, key go left or right accordingly, stops when key is found or a null child is reached. Average time O log n tree roughly balanced. Worst case O n degenerate tree. Insert, perform a search to locate the null child, where the new key belongs, then attach a new node, same complexity as search. Delete 3 cases. Case 1 node is a leaf, just remove it. Case 2 node has one child, replace node with its child. Case 3 node has 2 children, find the in order predecessor maximum of left subtree or successor minimum of right subtree. Copy its key into the node, then delete that predecessor successor which falls into case 1 or 2. Deletion also runs in O height time. Average versus worst case, if inserts are random, the expected height is about 1.39 log base 2n operations stay near logarithmic. If data arrives sorted, the tree becomes a linked list, height equals n-1 operations degrade to linear time. To keep the BSD efficient in practice, we often augment it with self-balancing schemes AVL red-black that guarantee logarithmic height regardless of insertion order. Height-balanced trees keep the height near log base 2 of n by enforcing stricter shape rules. AVL trees, named after Adelson, Velsky, and Landis. Balance factor of a node equals height of left minus height of right. Allowed values are -1, 0, or +1. If an insertion or deletion causes a node's balance factor to become plus or -2, rotations are performed to restore balance. There are 4 rotation types. Single right rotation, abbreviated RR. Single left rotation, abbreviated LL. Left-right rotation, abbreviated LR. A left rotation on the left child followed by a right rotation on the node. Right-left rotation, abbreviated RL. A right rotation on the right child followed by a left rotation on the node. After each rotation, heights are updated. The tree remains a binary search tree. Red-black trees, each node is colored red or black with 5 invariants. 1. The root is black. 2. Red nodes cannot have red children. There are no 2 reds in a row. 3. Every path from a node to its descendant leaves contains the same number of black nodes, also called black height. 4. All leaves represented as nil are black. 5. New nodes are inserted as red, then recoloring or rotations fix any violations. These rules guarantee the longest path is at most twice the shortest, giving a height h less than or equal to 2 times log base 2 of n plus 1. Rotations used are the same single left or right rotations as in AVL, but fewer rotations are needed on average because recoloring does much of the work. Analogy: think of an AVL tree like a tightrope walker who constantly adjusts foot placement, rotations, to stay perfectly balanced. while a red-black tree is like a person walking with a walking stick that lets them tolerate a bit more tilt before correcting. Both structures ensure that search, insert, and delete operations stay in big O of log n worst-case time. Explanation: recurrence equations let us express tree metrics in terms of smaller subtrees. Height recurrence for a perfectly balanced binary tree like AVL after rebalancing. H of n equals 1 plus h of open parenthesis n minus 1 divided by 2 close parenthesis. H of 1 equals 0. Solving gives h of n equals big theta of log n. Node count recurrence for a full binary tree where each internal node has exactly 2 children. N of h equals 1 plus 2 times n of h minus 1, n of 0 equals 1. Expanding gives n of h equals 2 to the power of h plus 1 minus 1, the perfect tree formula. Leaf count recurrence for a full tree. L of h equals 2 times L of h minus 1, L of 0 equals 1. Hence, L of h equals 2 to the power of h. BSD expected height for random insertion can be expressed using the recurrence. Expected h sub n equals 1 plus 2 over n times the sum from k equals 1 to n minus 1 of expected h sub k. Solving this yields expected h sub n approximately 1.39 log base 2 of n. These recurrences are derived by looking at how a tree grows. Adding a root creates 2 subtrees that are almost independent, so the total measure is the combination of the measures of the subtrees plus the work at the root. Solving them often by expansion, or the master theorem, gives us the asymptotic behavior that guides algorithm design. Prove the node count of a perfect binary tree of height h is 2 to the power h plus 1 minus 1. Base case h equals 0. A single node gives 2 to the power 1 minus 1 equals 1. Inductive step, assume true for height h minus 1. A perfect tree of height h has a root plus 2 perfect subtrees of height h minus 1. By induction, each subtree has 2 to the power h minus 1 nodes. Total nodes equal 1 plus 2 times 2 to the power h minus 1 equals 2 to the power h plus 1 minus 1. Given preorder a B, D, E, C, F and an order D, B, E, A, F, C, reconstruct the tree and write its postorder traversal. The first preorder element A is the root. In an order, elements left of a D, B, E form the left subtree, right of a F, C form the right subtree. Left subtree preorder B, D, E, an order D, B, E, root B, left child D, right child E. Right subtree preorder C, F, in order F, C, root C, left child F. The reconstructed tree has A as the root, B as the left child of A, C as the right child of A, D as the left child of B, E as the right child of B, and F as the left child of C. Postorder left-right root equals D, E, B, F, C, A. Analyze the cost of searching for a key in a binary search tree that receives sorted insertions versus random insertions. Sorted insertions produce a degenerate tree of height n-1. Search cost equals big theta of n linear. Random insertions give an expected height of about 1.39 log base 2 of n. Thus expected search cost equals big theta of log n. In the worst case, even with random insertions, the height can still be n-1, but the probability is negligible. These kinds of problems test understanding of definitions' ability to manipulate traversal orders and skill in asymptotic analysis, all core to data structures courses.